Hey guys, and welcome to another video in my series of university level physics videos. And in this video we are going to be kind of continuing our video series of thermodynamics. However, in order to get any further, we need to go on a bit of a slight detour. So we've kind of we've done the first, second and third laws of thermodynamics. And this kind of takes us up to about 1800s. So by this point we can kind of do things like steam engines and fridges and cool stuff like that. But it does go a bit deeper, thermodynamics. And in order to go any deeper, it's actually we actually have to go into the wonderful realm, or probably not so wonderful if you're like me, of statistical mechanics. And when I first heard statistical mechanics, I was like, what the hell is this crap? Like, it's very abstract at first. And at first I really didn't understand it or like it very much, to be honest. However, I do feel I'm at a point where I can probably explain it in a simple way. I know that it can probably be a little bit daunting at first when you start doing statistical physics, because often you've just finished doing thermodynamics, and then you're all of a sudden you're doing all this probability and canonical ensembles and partition functions, and you're like, what the hell is all this crap? So we're going to start a new video series today on statistical mechanics, an introduction to statistical mechanics. And we're going to start really nice and simple. We're going to make sure we're familiar on all the basics before moving on, because the maths can get pretty hefty in statistical mechanics. So we need to be prepared and we need to know what we're up against. So let's get started. So where do we begin with statistical physics? Well, statistical physics is all about probabilities, and it's all about what the probabilities are of certain particles. So let's say we have some particles here just sort of whizzing about. It doesn't necessarily have to be a gas, they're just sort of whizzing about. They might have this amount of energy, or they might have this amount of energy, or they might have this amount of energy. We really don't know. But what you can do is apply a probabilistic approach, so like be able to tell what the probability is of a particle having a certain amount of energy. And we call a certain energy level, we call it a state, and a state is a pretty important word when it comes to statistical mechanics. You need to know what a state is. It's basically a energy level. So for an example, say you have an atom with his own nucleus, and you have electrons whizzing around the atom. The electrons can occupy certain states, and so if it's in the shell that's closest to the nucleus, then it has this energy state. If it jumps up one, it has the next level up energy state. Of course, quantum mechanics tells you that these states are quantized, and this is what basically a state is. It's an energy level. And the way we like to kind of represent these states a lot in physics is you have sort of like a ladder almost. So you've got to kind of imagine a completely artificial ladder. And basically each rung of the ladder represents a certain energy. So let's just call this rung, let's call this the zero energy state. So what I mean by the zero energy state is if a particle has absolutely no energy at all, then that's the zero energy state. But what about this one right here? Well, let's call it a name. We could call it anything. Let's call it epsilon. Epsilon is a certain amount of energy that a particle might have. And so moving up, you can have 2 epsilon, 3 epsilon, etc., etc., and you could go on potentially forever. In classical mechanics, there's no restriction on how many energy states you can have for a certain system. Normally, the higher energy states are much less likely to be occupied, and that's one of the key things that statistical mechanics actually predicts quite beautifully, is that high energy states are less likely to be to be occupied, which is probably a good thing considering like high energy states. You know, if particles have a lot of energy, then we're kind of a bit fucked really, because then we'd kind of have X-rays coming down from the sun. And statistical mechanics does predict that these high energy states are less likely to be occupied. So here we go. This is going to be our basic model for this video. It's our kind of set of energy states. So let's do a simple example. Let's take the simplest possible example that's very easy to explain. Now we're going to have 3 different systems. I'll draw them in different colors so you can see which ones they are. So let's have system A right here. And these systems are absolutely identical. There's no difference between them. So let's just call this system A. We're also going to have an identical system. Going to have system B. And what I'm drawing here is I'm essentially drawing the energy levels of each system. So it could be, say, 3 pendulums or 3 boxes of gases, but the point is that each of them has a certain set of energy levels which they could occupy. And this is system C right here. So let's say each system has 1 particle in it. And this particle, it could be anything. It could be a proton, it could be an electron, it could be a neutron, it could be an anti-quark plasma gluon neutrino, or whatever the crap that is. I think I just made that up, not going to lie. And this particle, the point is that it can only take these energy levels. It can't exist in between. It can only take a certain energy level. And we're going to ask ourselves, what is the probability of a particle being in a certain energy level? Now, we're going to firstly say that let's just let these energy levels go on forever. In all three of these systems, the energy level just goes up and up and up forever. But that doesn't really matter. But let's say, for example, system A has this particle up here, up on this energy level right here. In fact, let's just make this easier and give these little numbers right here. So 0, 1, 2, 3. We're not going to bother with units, but if you want, you could attach some units if you wanted to. But this just shows the quantization, the discrete levels of this system right here. So system A has this particle up on level 3. What about system B? Well, let's say that system B also has it on level 3. And system C has particle on level 0. And so we're going to ask ourselves the question, how many possible ways of distributing a certain amount of energy? So let's say we have a certain amount of energy. Let's call it 6. So say we have 6 units of energy. How can we distribute these 6 units of energy throughout these 3 systems? And we're going to assume that these systems are what's called distinguishable. And we'll come on to what that means a little bit later on, because this concept actually becomes very important when it comes to quantum mechanics, because quantum mechanics says that particles are fundamentally indistinguishable. But for now, we're still in the classical realm. We're going to assume these particles are distinguishable. So yeah, how many ways are there of distributing 6 units of energy amongst 3 systems? Well, that you could count them all out if you really, really wanted to. But we kind of want it to do a little smarter way, to be fair. But before we work that out, we're just going to introduce a term. And we're going to introduce a term called microstate. This is quite an important term when we're talking about thermodynamics. And what a microstate is a permutation of sharing a fixed amount of energy. Let's just call it U for now. And so this is what a microstate is. And I've actually just drawn a microstate right here. One microstate has one microstate that I've drawn has system A with 3 units of energy, System B also with 3 units of energy, and System C with 0 units of energy. Now, the key word here is permutation. I've not written combination, and you need to understand the difference between permutations and combinations. And if I'm honest, I actually thought that they were exactly the same word for quite a long time, which was not a great thing, because when it came to statistical mechanics, I got very confused. So before I go any further, I'm going to tell you what the difference is between a permutation and a combination is. So let's take a really, really, really simple example. So let's say you've got the numbers 1, 2, 3. A permutation, in a permutation, the order matters. So 1, 2, 3, how many different permutations are there? How many different ways are there of ordering these 3 numbers? Well, you're going to have 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So there's 6 permutations, aren't there? 6 different ways of ordering the numbers 1, 2, and 3. And what is a combination? Well, the combination is still the same. You've got exactly the same numbers, 1, 2, 3. So that just counts as one combination. And so you can say that there's 6 permutations for this particular combination. A different combination would be 1, 2, 4. And again, you'd have 6 different ways. Take maybe a 4-digit number, 4022. What have you got? You've got 2 2s, a 0, and a 4. To be honest, I can't be bothered to work out how many different permutations there are. But there is certainly only one combination. So that is basically what the difference between a permutation and a combination is. Think about it, maybe if you're playing a game of cards, each poker hand is essentially a combination. Because it doesn't really matter what order you have your cards in, does it? It doesn't matter if you have king, queen, jack, queen, ace, or queen, queen, ace, jack, king. It doesn't really matter. That's a combination. But if you're talking about permutations, then you obviously have many more permutations than combinations. So always remember, permutation is the bigger number than combinations. So that is what a difference between a permutation and a combination. And a microstate is a permutation of sharing a fixed amount of energy U. So I've drawn out one microstate. This 330 microstate, we can just give it a temporary label. We can just call it, 330 right here. And you can probably go through and work out all the different microstates of sharing this amount of energy. And if you do that, in this case, you've got 3 systems and you're distributing 6 units of energy, then you'll actually find that there are 28 different microstates. And we call the number of microstates, we give it the symbol omega, and we just simply put a little subscript NU right there. N is the number of systems, or the number of particles if you want, and will become the number of particles when we apply this to thermodynamics. And U is the amount of energy. So in this case, N equals 3, U equals 6. So you guys are probably wondering, how do you get 28 out of 3 and 6? How on earth did you know that it was 28? Well, there is actually a formula, which again, I'm not going to derive, but it's a pretty useful formula, and it is given as the number of microstates, omega, Nu, is given by N plus U minus 1, choose U. So this is a bit of statistical notation. You guys probably are familiar with what this brackets is. It's basically the binomial coefficient. It basically means N plus U minus 1 all factorial over U factorial multiplied by N plus U minus 1 minus U factorial. So you remember 6 choose 2 is equal to 6 factorial over 2 factorial times 6 minus 2, which is just 4 factorial. and that's the binomial coefficient. It's the n. It's often called NCR right there. That's what it is in maths, but here in statistical physics, this is what the number of microstates is, and it's this formula right here. Pretty handy formula. So actually, if you work this out, then in this case, you're going to end up with omega 3,6 is equal to, well, 3 plus 6 minus 1, choose 6, which is equal to 8, choose 6, which is equal to 8 factorial over 6 factorial times 2 factorial. And you guys know what factorial means, right? It's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, etc., etc. And if you do that, you end up with 28 being the number of microstates. And so that's quite a handy formula to work out the total number of microstates in this system right here. So what's next? Well, we're going to make a postulate right here. And we do this a lot in physics. We like to make our postulates. And we're going to say that all of these microstates, all of these 28 microstates, all of these 28 different ways of sharing this energy U are equally likely. So how are we going to write that? Well, we're going to write that as P, where P is the probability of a system being in a particular microstate, is equal to 1 over the number of microstates, 1 over omega, which seems fairly obvious. There's no bias, so we can assume, for the moment at least, that the probability of a system being in a certain microstate is exactly the same for every different microstate. So 330 has exactly the same amount of probability as the 411 microstate, or the 501 microstate, or the 321 microstate. They're all equally probable. All the 28 different microstates are equally probable. Now, as is the case with a statistical approach, there is one thing that comes up a hell of a lot in statistics, and that you need to know, and that's pretty important, and that is that every single possibility, the probability of every single state, must always add to 1. So that must mean that the probability of every different microstate must always add to 1. So in this case, we've got 1 over 28 plus 1 over 28 plus 1 over 28. How many 1 over 28s are there going to be? Well, there's going to be 28, obviously. So if you add 1 over 28 times, you're going to get 1. So all is well. But that's a pretty important thing, and it's called normalization. And that is the condition for any sort of probability. Any time you talk about probability, you must know that the sum of all probabilities, must equal 1. That's very, very important, and we'll be using that condition a lot to derive lots of useful, cool stuff. So that's a little introduction to statistical physics. But I'm actually going to go back to entropy, and I'm sort of going to parachute in an equation that might look a little bit weird for the moment. Might be a bit weird to introduce this now, but it will become very clear how this definition, this starting definition, ties in quite beautifully with thermodynamics. And you guessed it, it's all about entropy. We are going to define a statistical definition for entropy. Now, you remember what I said about entropy in one of my thermodynamics videos? I said that it's actually a measure of disorder. It's actually a measure of the amount of disorder. And so what can we call disorder? Well, the more different states there are that you have of a certain system, the more different microstates, the more disordered. And so what Boltzmann did, our old friend Boltzmann, who we're going to be talking about a lot, he defined entropy to be the Boltzmann constant multiplied by the natural logarithm of the number of microstates. So you're probably thinking, what the hell, why have you just written this? Well, Boltzmann did derive it, but we're actually going to start with this definition of entropy, and we're going to sort of work our way back to thermodynamics, if you like, and we're going to work out how we can get from the entropy back to what we thought the entropy was back in thermodynamics, which is, of course, change in heat divided by temperature. So this is just a definition for now. And so basically the important thing is that this is just a constant right here, kb, which is of course 1.381 times 10 to the minus 23. It's also there just to keep the units all good. And so it's the entropy is basically the number of different microstates of a system. So this is just a definition, and this is actually what's called statistical entropy. And we're going to actually show a bit later on that it's exactly the same as thermodynamic entropy. It's just two different ways of representing essentially the same thing. But yeah, this is just a definition we'll work with for now. So we have a few problems right here. It's actually very hard to calculate what omega is. I mean, I told you the formula before, but in a massive box of gas, you can't possibly work it out all the time. It's very difficult to calculate. Yeah, you just don't want to do it, basically. We're actually going to need to do some maths to get somewhere a little bit better than this. And secondly, it's also not reasonable to assume that the energy is fixed. There are actually different types of what's called ensembles, and they're kind of a bit like what I was saying about open systems and closed systems. In statistical mechanics, we call them ensembles. I'll just talk you through the three types of ensembles that you'll need to know about. So basically, an ensemble is a system of states, basically. It's a set of energy levels, but instead of one, you have several. So actually what I drew earlier with these three different systems, this is actually what's called an ensemble. So say you have this particle in here, in here, and here. This collectively is referred to as an ensemble. You might hear it called an assembly as well, but yeah, basically it's a statistical way of defining what we defined before, basically a box of gas which can be either in contact with heat or particle bath or anything like that. But it's just we call it something slightly different in statistical mechanics. And so what are the three different types of ensembles? Well, there is the microcanonical ensemble, there is the canonical ensemble, and finally the grand canonical ensemble. We're not going to come to the grand canonical ensemble for quite a while, but yeah, so these are the three different types of ensemble. And basically the microcanonical ensemble has a fixed amount of energy. The energy is fixed, and it's basically analogous to a completely closed system in thermodynamics, which means that no temperature can get exchanged, no heat can get exchanged, you can't do anything. The system is completely closed, so nothing can get in or out. The canonical ensemble has a well-defined temperature at any point. It's similar to basically what we were talking about a lot of the time in thermodynamics before we allowed the particle number to change. And so basically energy can flow in and out of the system, so the internal energy can change according to thermodynamics. However, the particle number cannot change. That is the canonical ensemble. And finally, the grand canonical ensemble, well, basically that is exactly the same as an open system, and energy and matter can flow in. And the grand canonical ensemble is by far the hardest, and so therefore we're going to come on to it last. But yeah, so that is basically the three different types of ensembles, and it's just a kind of fancy way of labeling the different types of system, basically. So what are we going to do with this Boltzmann entropy that we've got right here? Well, we're actually going to make an approximation, and to do this approximation, we need to make another definition. And this definition is what's called a macrostate. And what a macrostate is, you might have noticed that a lot of these microstates that I was on about earlier, so say you have 0, 3, 3, you might notice that there are lots of different ways of ordering this set of numbers. So you could have 303, or you could also have 330. Now, this is actually a combination, pretty much. The definition is very similar. A macrostate is just like a combination of numbers, whereas the microstate is, of course, a permutation. And so this right here is collectively one macrostate. It's the macrostate that has two lots of 3s and one lot of 0s. And so that is how you kind of define a macrostate. It's a little bit harder to write than the microstate. But yeah, that is the macrostate. And we tend to give the macrostate multiplicity the symbol W. And so in this case, W is simply equal to 3. It's not the number of macrostates in total, it's the number of microstates per macrostate, if that makes sense. So in this case right here, we have 3 different microstates, but we can see that they're all comprised of the same numbers, and so therefore this is a macrostate. Simple as that. So it's kind of like a way of grouping together certain atoms, certain molecules, pretty much. And the probability of it being in a particular macrostate rather than a microstate is, rather than 1 over omega, it's W over omega. So what's the probability of it being in this macrostate right here, this collective macrostate? Well, W is 3 and omega is 28. So we can see that the probability of being in this macrostate is 3 divided by 28 in this case right here. So that is what a macrostate is. It's basically a way of grouping together microstates. Now you can probably imagine that macrostates are pretty hard to kind of label and quantify. The way we do it is we specify a macrostate by the occupation number of each state. So let's just draw it out just so we know what we're talking about. So here's our set of energy levels yet again, and let's carry on with this macrostate of 2 3s and 1 0. So we have 1 0 and 2 3s right here. So this is 0, 1, 2, 3, 4, and so on and so forth. So this is a macrostate right here. But of course we have 3 different microstates for this macrostate. And so the way we write this is that the number of particles in energy level 0, which we denote by the symbol N0, is equal to 1. So this is the number of particles in the bottom energy level. So this little subscript here is the same as this energy level right here. But this number here is just the number of particles in that particular energy level in this particular macrostate. So that is N0. Let's just carry on and go through them just so we're very clear about what we're doing. So how many particles are in energy level 1? Well, 0. How many particles are in energy level 2? Again, 0. But what about energy level 3? Energy level 3, we can clearly see that there are 2 particles in this one. And so, well, there we go. We've used up all 3 particles. And so with our n equals 3 system, then we have done them all, so we can assume that there's nothing more in the rest of these energy levels. So that is how we denote a macrostate. We denote it by the occupation number. So we can simply write that n is simply the sum over j, where j is the energy levels right here, from j equals 0 to some point j. It could be infinity, it might not be infinity, you never know, of n j right here. So in this case we've got it to write 1 plus 0 plus 0 plus 2. So that again is equal to 3, which is of course the number of particles that we have. So all is well so far, all is well. So that's N. What about the energy U? How can we work out what this is from in this simple example right here? Well, we said that the N is 3 and U is 6 before. So how do we show that it's 6? Well, U we simply write as the sum. It's the total energy in the system is the sum of the energy value multiplied by the number of particles that are in that particular energy value. So sum of EJ multiplied by NJ. It's simply the sum over all of the different energy states weighted by the number of particles that are in the energy states. It's a very common thing that you'll see quite a lot. So this is a sum from J equals 0 to J. Again, we don't know what J is. It could potentially go on forever, but in this case we've just got nothing after this point here, nothing higher than the 3 level. And so what would this be? What will we get if we expand out this sum? Well, if we've got one particle on the 0 energy level, that's not going to contribute anything. So we've got 0. N equals 1 level, no particles, so that's just going to be another 0. N equals 2 level, no particles, so just another 0. N equals 3 level, well, the energy of the N equals 3 level is, well, 3. This is the energy 3, the third, the 3 level, if you like. And how many particles have we got? We've got 2. And so that is just going to equal 6, which is the amount of energy that we had. So all is well. All is well. We can derive what N and U is if we have this sort of state here, we know what N and U is. And these formulas are quite important, and therefore I will just put a little highlight around them. And there's just one thing that I missed out, and that is basically how did I work out that there were 3 microstates for this particular macrostate right here? Well, W right here is simply equal to N, which is the total number of particles, in this case it's 3, factorial, divided by, now this is where it gets a little bit weird, we're going to have a sort of an infinite product, basically, and we're going to write N0 factorial multiplied by N1 factorial multiplied by N2 factorial, N3 factorial, and so on and so forth, right the way up to the infinite energy. But as you're hopefully aware, 0 factorial is equal to 1. So don't worry about this whole divide by 0 problem. It's not a problem because we've put a factorial in front of it. And so therefore any 0 terms in the denominator right here will just go to 1. And so how do we work this out? So we've got so in this case N is 3, so we're going to have 3 factorial on the top. There is 1 particle in the 0 state, so we're going to have 1 factorial there. Nothing in the N in the 1 state, nothing in the 2 state, but we're going to have 2 particles in the 3 state, so therefore it's 2 factorial as well. So these are multiplied, and we're just going to get 1 for the rest of these. There's just going to be an infinite number of 0 factorials, and no matter how many times you multiply 1 by 1, you're just still going to get 1. And so what's this? Well, 3 factorial is 6 divided by 2 factorial, which is 2, which equals 3. So this is a handy way of calculating the number of microstates per macrostate. We often give this term W the label the macrostate multiplicity. So it's the number of macrostates, the number of microstates for a given macrostate. And I hope that makes sense. So on to the next bit.